with this, we would like, Ali and I would like to start the panel. And indeed, for this, it would be great if if the panelists can switch on their cameras, which would be Nathan, of course, as one of our speakers, but also Eric, David, and Peter, of course. Sorry. Yeah, switch on your camera. I quickly introduce you, but I keep it short because we want to give you the opportunity to briefly tell about your work as well. The main idea, just to set that up for this panel, is to discuss a little bit how software or design automation can help in the development of quantum computing. What are the challenges? Where are we at the moment? What do we have to still address? Where we want to go? Where would you see us in the next years? So we have a couple of questions prepared, and for this, we're really happy that we've got a good spectrum of panelists here. So Nathan Ordo had been introduced and already gave his talk. Then we have Peter Salinger, who covers the programming language part. He's also a computer scientist from Dalhousie University, but also actually mathematician and computer science, developed a lot about the semantics of quantum programming languages. And we've got David Venturini, who is covering kind of the application part. He is with the NASA Quantum AI Lab and the University Space Research Association, a huge organization doing a lot of work with lots of companies, research agencies, with NASA, DARPA, NSF, many others. And I think there's also congratulations in you because you just got appointed in USAR fellow. So congratulations to that. That's a really cool accomplishment. And then we have Eric. And for Eric, I hand over to you, Ali.
Okay. And then last but not least, we have Eric Peterson. He's a mathematician. He got his PhD from Berkeley in math and then did a postdoc in math at Harvard. You can imagine that having an expertise in geometry and algebra is pretty useful for quantum compiling. So then he continued to contribute quite significantly to the compilation efforts at Rigetti, IBM, and now at AWS Center for Quantum Computing. Okay, we're very happy that you're all here. Thank you for spending your Saturday with us. All right, so I'll just start as an icebreaker, I guess, as to get the conversation going. So we're in this workshop around the theme of co-design. And I was wondering if each of you could, briefly talk a little bit about your experience with co-design, maybe something interesting from your own research or something else you've seen somewhere else that kind of relates to this idea of co-design. I think here we're all kind of theorists, but is there anything interesting that you can tell us from your past experiences that kind of was an interesting result that could not have been possible without this idea of co-design? And who wants to start?
Well, I'll get started. I think there's a couple of things that I've run into. The first, which I mentioned during my talk, was this question about what you can end up doing if you provide yourself a broader range of gates inside your gate library than what you normally end up getting. And this is something that we noticed that if we wanted to do a digital simulation of bosonic systems, because we didn't have to do square roots or many of the other operations that we needed to compute with qubits. Just the native bosonic operations had precisely the thing that we wanted to carry out. The costs could be orders of magnitude lower for near-term applications of it. That's one thing. Another thing that actually is really kind of interesting was the realization that we had for a lattice gauge simulation, that actually the Gauss's law constraint can be used in order to be able to identify bit flip errors that happen in the system. And so that ends up suggesting that actually, normally what you end up doing if you're envisioning something like a short code, is you concatenate a bit flip and a phase flip code. It suggests that the application already natively has the symmetry of the bit flip code built in. So if you're applying error correction to that application, you don't need to redundantly build that symmetry. It's already got it. So the other thing that I wanted to mention is that people spend a lot of time talking about the co-design on the hardware and algorithmic level, and that's an important aspect of it. But there also is this co-design between the quantum error correction and the application that we need to consider, because after all, if you view it from the perspective of the software stack, usually the algorithm isn't actually seeing the hardware. Normally what it's seeing is the quantum error correcting code that it's running on top of. So we really kind of, those have been some examples of it, but I'll leave it to other people to give more.
Yeah, thank you.
I'll go second. One thing about my work, I am still mostly focused on the NISC era, and I'm one of those that still has some hope that we could get something out of it. But my hope is definitely in co-design, like meaning that everything I have seen and done in the last few years requires essentially hardware efficient methods in order to extract any signature of qualitative advantage and hopefully quantitative one day. And so when I look at the opportunities for us in the near term to exploit noisy quantum systems for algorithmic advantage or learn something in terms of, like, for example, analog simulations or machine learning methods that could be also leveraged for optimization, I do see the requirement to really go and co-design with hardware developers. One example that I typically encounter is how can I leverage the imperfections that I see in the machines to and bake them up in the algorithm. One example is in trying to innovate on quantum optimization and QAOA. We recently published work on an ansatz. It's called my God, we have so many acronyms. Quantum alternate mixer phaser ansatz, where we use XY gates as part of the mixing process in the algorithm, as opposed to the X gates. So those are natively present, for example, and calibrated as part of some transmonic interactions in multiple superconducting processors. And we work primarily with Rigetti. But one thing that is not in the paper and will be in some paper or talks soon is that if you take the XY gate nominally, it's a gate that conserves symmetry that you might even want to use for your algorithms. But of course, for noisy device, you can't really rely on any conservation for real because you have all sort of errors that catapults you out of the logical subspace. So actually, we're going to use, for example, that gate as a mixer under the assumption that does not conserve that symmetry in some of the experiments. And as a matter of fact, that's an advantage in some extent because that symmetry might actually mess up with the probability of success if you're solving a problem that does not need that constraint. So this is an example where you kind of flip the thinking and say, okay, the device is imperfect, but we can leverage that imperfection to design an algorithm, and of course, everything requires a lot of error mitigation in the NISC era, but still you can proceed going forward. It requires co-design.
Excellent.
Maybe I'll go next.
Peter, go ahead, please.
So I sort of occupy another niche because I almost entirely work in the post-NISC era. So my thing is the design of programming languages and software engineering. And of course, programming languages the main thing of software engineering is to build large systems reliably, like the kind of situation where you have, very, very large programs that are assembled from many different parts and you want them, to be correct. So so that's sort of post-NISC, right? So I'm designing programming languages for for that future time when we have universal error-corrected quantum computers that can do everything. So co-design is probably more directly applicable to the NISC era right now, where you have to squeeze the last bit of things that you can out of the hardware that you have. I think it's also going to be relevant in the post-NISQ setting, just not as urgent maybe at this point. But of course, when we have programs that run for years or use, trillions of gates or whatever, even in some universal error-corrected regime, we're still going to be interested in reducing the resources that those algorithms take, obviously. So that still means that you might have to take specific advantage, like Nathan was saying, of specific features of an algorithm or specific features of the hardware, or that where there's some steps that you can basically optimize away. So if for example, something I sometimes think about is, what if you have an algorithm, with two subroutines, but one of the subroutines is much more robust, is sort of naturally more robust against errors than the others? What kind of trade-offs do you have to make, moving most of the error into this component or that component? Maybe there's some parts that don't need to be error corrected as heavily, and so on. But I don't know any actual examples of that. So just the kind of thing I'd be thinking about.
I'll give an answer. I hope you forgive it for being a little bit generic. My impression of the sort of state of quantum computing up until even just a few years ago is that all the groups involved in building a quantum computer were sort of relying on each other to provide very specific like features that they were going to use, and to otherwise be able to treat each other as a black box. Like the device designers were going to provide devices with particular characteristics. The experimentalists were going to use those characteristics to be able to tune up a very particular set of gates. The people working on like compilers, that kind of thing, were going to rely on the existence of things like C-naughts to develop sort of very particular compilation routines all the way up the stack, so that you could finally say, at last, we have a quantum computer. Everybody went about this slightly differently, and we're now in this sort of second phase or second generation where we have these devices laying around. They're all slightly different from one another. And in order to push things a little further, you have to be willing to open these black boxes and look at the details of what you built and be cognizant of sort of what the people around you are doing. So for instance, Nathan mentioned this example of enlarging your gate set. What that means is, of course, dependent on the device you have. And so you have to be aware of those kinds of details to make use of those kinds of ideas. And that's like being able to both pay attention to what's around you and also to indicate if you could give me this, then I could squeeze more performance out of my part of the system. That sort of bidirectional flows, and that's what we're here for.
Yeah, sounds great. Just to put a little bit in perspective, this also actually all you said is a good example for the next question we want to ask, because Nathan, you made up the point that the co-design not only between software and hardware, but also between software and error correcting. David on how to deal with imperfection. Peter, you aim for the big applications for the post-NISQ area, and Eric, you consider the broader picture. For all those aspects you covered, what would be your main benchmark? Or do you have a good example, a benchmark, which on the one hand side showcases, okay, that's how far we are already, but also maybe illustrates a little bit those are the challenges which still lie ahead of it for those different aspects? Like Peter, for your big things, how do you evaluate your big complex language or your language, whether or not they're able to cover big complex systems so far, and then vice versa? Then also for David, Eric, Nathan, how you evaluate for your aspects you want. Maybe Peter, you want to start, and we start from the top, and then maybe go down to the smaller systems down.
Well, for big computations, obviously you can't run them currently, and you also can't run them on simulators. So you basically can't do anything except develop, I guess. What you can do is you can write the programs, even though you can't run them. You can do resource estimation on those programs, because we want to know how much it's going to cost to run them one day, right? And you can also do some verification. So using formal software methods for reasoning about programs, because one big issue is you could spend trillions of dollars building a universal quantum computer, but then actually debugging quantum programs is very hard. Typically you turn it on, it runs for a week, it's coherent. You can't just stop it and measure something, to make sure it's on track. At the end, it might not give you the correct answer, and then actually pinpointing the source of bugs is very difficult. So one thing that we can do now is sort of develop formal methods for proving the correctness of quantum programs, things like that. I mean, I don't think it's going to become relevant until probably several decades from now, or at least 1 decade from now, when we actually have large computations to run. But it's good to kind of get a head start, I guess, on thinking about these things.
Completely agree, particularly when we consider that we still have a design gap in the conventional realm. It's better to start early on these kind of developments. What kind of benchmark have you? I mean, I don't know, David, Eric, Nathan, what is a good example showcasing where you are and where are the challenges?
Well, okay. So if you want the best benchmark, one of the things you got to pay attention to is every benchmark will tell you different features about the system. And unfortunately, I don't think that there's really kind of like the one benchmark to rule them all. What I would say is, my favorite benchmark, if you can do it, is gate set tomography. Gate set tomography kicks ass. It tells me just about everything that I need about the system to be able to predict its performance. If I can't get that, the next best benchmark I like is something like RB. RB doesn't quite give me as much information, but it gives me a pretty darn predictive model about how well the system performs. People have talked also about doing holistic benchmarks that end up taking a look at the performance for testable algorithms on the system. And those potentially are valuable, but unfortunately, I think one of the big challenges about it is quantifying the information that you end up getting out of the benchmarks and being able to say, from some of these system level benchmarks, what aspects of the hardware would you need to say improve in order to be able to kind of spiral around and continually get better. It doesn't as easily tell you what the delta is from or what the bottleneck for the performance is for the system level benchmarks. But perhaps the most interesting benchmark, I think, is probably like the least scientifically useful. I would say that, if you want to know when quantum computing has finally come of age, really for me, the benchmark is the very first paper that, a computational chemist publishes who doesn't give a rat's ass about quantum and ends up using it because it's the only way for him to solve his problem. And, once we've hit that point, then I think we'll have hit the value threshold for quantum computing. But, kind of at the moment, thinking about the right way to benchmark your quantum devices, it really is this trade-off that you want to perform between the level of detail with which you end up understanding the system, the amount of experiments you need to do, and the amount of classical processing you need to do in order to be able to interpret those results. And I think, this is a reason why QCVB is still an open field, because we don't have the final answers quite yet on what the best ways to benchmark a quantum system is.
Agreed. Yeah, David.
Yeah, no, I 100% agree with everything Nathan said. And I want to remark that in many of the projects I'm involved, like DARPA ONISC, or there's NSF expedition on quantum inspired algorithms, or even in the quantum benchmarking. I mean, sometimes we do not have the luxury on experimental data to really try to understand it to the level of gate set tomography or even randomized benchmarking. Even sometimes it would be completely maybe not appropriate due to the complexity of what we're trying to do. And if you do believe in some sense that you might have a chance to have a system which has some quantum effects that are really providing some computational value, then maybe you can lower the bar and try to detect those effects somewhat without really without the requirement to understand what's going on and modeling the system appropriately. So if you consider the system as a black box, sufficiently coherent with some crosstalk that you did not calibrate, but you somehow are able to tame by parameter setting procedures, so a very quantum machine learning approach, then maybe what you can do is try to look at some, for example, tomography of single qubit reduced density matrices to see if there are coherences there, so the ability to tunnel after the execution of an algorithm, or go on the higher order correlations, but not, of course, of the entire algorithm, because that would not be practical. And in some sense, this approach is inspired by what quantum annealing tried to do in 2013-14, like trying to detect, is there multi-particle tunneling happening? I mean, I don't know the value of it, but I want to see whether it's even possible in principle after a certain mess of interactions to observe a tunneling event, right? So in some sense, I believe that even on digital algorithm executed in the NISQ era, we could be okay with witnesses of quantumness at some point if the circuits are sufficiently complicated when it comes to validate the quantum aspect of what we're doing. But when it comes to validate the advantage, all I want to say, I completely agree that the final stamp of quantum advantage is business value demonstrated by someone that doesn't give a rat's ass about quantum and uses quantum. But just an element of thought, like a lot of benchmarks out there, they do kind of ignore the complexity of parameter setting, and you can always trade off between how much you fine tune your things and the performance you have if the system is not too noisy. And I think that the entire benchmarking of a noisy device needs to start caring about how the computational cost of discovering the parameters that we used for publishing the results, because there's a lot of misleading, in my view, like results that are very impressive, but at the end of the day, they hide a lot of many weeks of postdoc times in finding the perfect schedules of the perfect angles or parameters of their circuits. So,
perfect. Maybe Eric, a couple comments from your end.
Yeah. I'll come at this from a somewhat different direction. I definitely don't have a proposal for a numerical benchmark for these kinds of things, but the way that what I'm drawn to as I look at these things is some kind of measure of expressivity. Like there's some algorithm that I would love to run. I have to be able to write it down in some way, and then it has to flow through this long chain of different tools until it finally runs on some manner of hardware. And it's interesting to study where that presumably small bit of information that you started with, the computation you'd like to perform, explodes in size as it travels down this tool chain. It gives you some kind of measure of how well adapted these interfaces with the different steps in the chain are to one another. And that's that's what I would like. That's what I like examining the most, and that's what I would want to push on the most.
Maybe if I make just a quick follow-up, so that I completely understand that, sort of in order to, as you said, open the box go through the entire software stack, open the box. Does it also mean that in between it also okay that in order to check these interfaces, some sort of artificial benchmark? We talked about okay, not every benchmark is perfect yet, but is it okay as an intermediate step to evaluate the power of the respective software tools of the compiler, so that it also is okay to have some not that practical element benchmarks as an intermediate thing in order to foster the development of those software?
Yeah, totally. So again, I don't have something to propose in that direction, but it's definitely true that if you think that the ultimate end goal of a quantum computer is doing some physical chemistry simulations, and you start with that, and then you're trying to examine the interface at the bottom level, and you've already incurred a couple of exponential explosions along the way, then you're going to find it difficult to interpret what's going on. It's intermediate benchmarks make perfect sense.
Perfect.
Okay, so for the next question, I think what I wanted to, I guess it's kind of an open-ended question, so take it as you will. But so this session's name is Software Tools and Design Automation. And so I guess the way I interpret it is, to make progress in quantum software, quantum compilers, design automation, we need a whole bunch of theory, and we also need good software implementations of those. So, I mean, we just heard from Martin about Q#, and Azure ecosystem. We have representatives here, Peter from Quipper, Eric has worked extensively on QuillC and other software, and so on and so forth. So I guess one thing I wanted to kind of get your take on is, given all the theoretical advances that have been made in the past few years, and also all the software implementations that there are, I mean, we've made a lot of progress. Well, is there something that you see as like a glaring hole or missing piece that you think should be addressed in the next 5 years, let's say, as we go towards larger systems, maybe early examples of fault tolerance, or just maybe generally your open favorite theoretical question. There are a lot of people in the audience here that are researchers, and maybe it would benefit from your take on what are some interesting things to work on, either on theory or in software, in quantum software generally.
So, yeah, how about I be loud as usual and start things off with at least some relevant problems that I would like, I have at least wished that a computer could solve for me in the past. One of the biggest ones is the error balancing problem when you've got a quantum algorithm. Ideally, often, especially if you're looking at an algorithm like quantum simulation, and has a whole bunch of approximations going all the way down to, rotation synthesis and all the way up to, the Trotter decomposition or whatever you're using for the simulation. All of those errors have to add together, and it in some way that affects the outcomes of the observable that you're measuring. And at present, in order to optimally trade off the costs of all of these things, you need an expert who sits around and knows how to track the errors of each of those components and puts it together. If we really want to democratize these types of processes, we need to make it so you don't need myself or Dominic Barry or Guang Hao to be able to solve this. Well, you really need a computer to be able to stand in for other people to be able to do this. So that's one thing that we need. It's the epsilon pushing. The next part that I think really needs to be addressed is the fact that, at present, it's the language used in quantum error correction is so radically different from the language used in quantum algorithms that it's very difficult for algorithm specialists to be able to jump in and actually translate their stuff down through the error correction layer to the software. And, it's unrealistic to expect every single time you want to do a compilation that you'll have to get an error correction expert to be able to lay out the surface code in an appropriate way to be able to do this. Microsoft, of course, has obviously made some strides towards this, but, we need to really be able to have the ability to lay out all of the circuitry needed for popular codes like the surface code in order to be able to actually do all these things, because, well, there's absolutely no way that you can get the average algorithms expert to lay out their own T-factories, for example. So that's another thing that I think is a major challenge that we end up running into. Another challenge, or another thing that I think is becoming increasingly apparent, is that as we start getting to the point, I'm a strong believer that to show any kind of value will almost certainly need quantum error correction in quantum computers. And at present, unless the gate fidelities radically improve, we're going to need a lot of quantum error correction. And so if that's the case, and we need about 1 million physical qubits, like Microsoft, as well as my own studies have shown, we're kind of pushing the limits of what you can likely fit inside a single dilution refrigerator. So thinking about how to distribute an algorithm over multiple quantum processors, and best yet, develop the software tools to be able to intelligently distribute for loops and other kinds of logical structures over multiple quantum processors is really important. And this is going to be doubly important also for systems like Quantinium, where there's only a limited number of qubits that you can have per interaction site, but shuttling is sort of required in order to be able to get the whole thing working. So those are some examples, I think, of stuff that I really would love to end up having. But I guess the final one, and this is a little bit of a, obviously speaking to my own obsessions, but given how many algorithms can be thought of as particular cases of the block encodings or the singular value transformation, it would be beautiful if a quantum programming language had nice paradigms to be able to express those types of concepts. Because if you could do that in a cool way, it would make expressing a ton of quantum algorithms far easier than it currently is. So those are a couple of things that I would love to see.
Great, thanks for that nice answer. Who's next?
There was a question. Somebody raised the hand, so I don't want to. Okay, maybe.
I think that this was just in +1, I guess. And then there is a question in the chat. We will come to that, but maybe what is like the big challenges? Nathan already mentioned 3 of them. Any further additions? It doesn't have to be that each and every time everyone says something, but if you have an important decision, now is a good chance about what are the 4th challenge and the 5th challenge, maybe.
I had 3 + 1.
Wait.
Well, so first of all, I agree with all or most of what Nathan said. Certainly the problem of error distribution, I think, is an important one, because when we've gotten now we are to the point where we actually need to worry about the constant in front of the big O notation, right? So when you're just doing an estimate to know if your algorithm is polynomial, super polynomial, you don't really care. You do like the analysis thing. You just use epsilon over 3 everywhere for 3 different errors, and then you add them and it's less than epsilon. But clearly this isn't going to be optimal, right? On the other hand, I find it's really difficult to do in theory. And maybe it can't even be done in theory. Maybe you have to run your program on the computer and do some kind of tomography to find out what the actual errors are in practice, because they're always going to be much smaller than your upper bounds, which you get from some kind of estimation, right? So the errors are most likely to almost always be smaller than what you can prove them to be, right? And so it's something you may that's where co-design probably also is important, right? You run the algorithm, you measure the actual error that happened and how adjusting different parameters affects the error, and you do that. The other thing I wanted to say is, so as a programming language designer, I'm interested basically in 2 things, right? One of them is, how do you get an algorithm from a research paper into a programming language? There also, Nathan said it would be great if we had some primitives that could do, block encodings or algorithms based on block encodings somehow in an intuitive way. That would be great. The other thing I'm interested in is, how do we get the program from the programming language to the hardware, right? Or by hardware, I don't mean the physical hardware, but maybe some kind of lattice surgery layout or something like that. And you're right, that's not something every quantum algorithms specialist is going to know or even want to know about, right? So there needs to be a separation of concerns. So that would be great to have automated, if we had better automated tools for actually compiling, like getting, for example, there should be some tool that decides how many T factories you need, where those T factories should be, how fast they should be, how they should interact with the tiles, and the surgery operations and so on. And I think there's important trade-offs there that are still that still need to be explored. So the standard, as I understand it right now, it's sort of the state of the art in surface code and lattice surgery is you apply this sort of Litinsky method where you basically it's a kind of measurement-based quantum computing where you never do a Clifford gate. You just kind of keep track of them, and then you adjust the axis for future measurements, and you kind of save all the Clifford gates until the end, at which point you no longer have to do them because you just do measurements. I'm wondering, this is a really great method for doing the computation, but it does kind of mess up parallelism. And we have a lot of quantum algorithms that have a lot of inherent parallelism. For example, if I want to do a controlled rotation gate, there's a way to do it with a C0, and then basically you have 1,000 Clifford plus 2 gates on one qubit and 1,000 Clifford plus T gates on another qubit, and it's completely parallel, right? And for 1,000 steps, and then you do another C0, stuff like that. I wonder if the structure of the algorithms must be, or the structure of the circuits must sort of be taken into account when you compile to the surface codes. For example, if you just do the standard trick, you can't do anything in parallel because every T-gate could potentially affect all of your qubits, right? So maybe there's a trade-off where sometimes it's a good idea to do some Clifford operations, and then, in order to set up things that you can parallelize them. I don't know. Anyway, that is just an idea of a problem I would like to see solved. Maybe someone's already solved it.
Yeah, let's then. I mean, we're writing a report at the end of this workshop, so maybe you can place this question there as well if you like. If you, Eric, if David, if you have no further additions, I would like to do a follow-up a little bit on what has been said before, and also goes all along where we may want to go. And in fact, maybe a little bit provocative, maybe a little bit too long vision, but you mentioned a lot that already, the guy who develops the quantum algorithms and the guy who develops the surface code for error correcting, they hardly can get together, or they have some sort of it's hard to make that available. Maybe we can take that one level further. Right now, I would say, obviously, we have decades of compilers in the classical realm, decades of programming languages, of program language expertise, and maybe we don't get all these quantum workflows that easily. So my question is a little bit like, when we go in this development, making it a little bit more intuitive, how much quantum expertise do we need? How much of the entire software stack can we do, or can we do it in a way that we can sort of this entire quantum design flow and software flow, can we do that in a way that shields as much as possible quantum computing related stuff or quantum specialist stuff from the end user? Is this possible? Should we aim for that? Maybe a little bit in the sense there's a development going on in the classical world called low code, that we not even have to understanding with programming in the first place in order to realize software applications. Is this something possible in the near future, or at least in the long run, for quantum computing as well, so that people can develop quantum applications while at the same time we're shielding as much as possible from the non-intuitive quantum computing stuff from it? Is that possible? Should we aim for that, or is that totally unrealistic? What do you think?
I think we can have software in the medium run, or maybe long run, where a chemist would enter a molecule or take a molecule from a database. Martin gave this example, I think it's caffeine. You just pull caffeine.txt from chemistry.org or something. And then you can ask certain questions about that molecule, like what are its excited states, what is its ground state, what is the energy gap or whatever. I don't know what it is that chemists want to know about a molecule. But I mean, I could imagine we can have software like that. But it's just like, I think my feeling is that this, at least in the foreseeable future, the software developers will still have to understand quantum computing, but maybe not the users of that software if it's in a sufficiently specialized domain like chemistry.
I think, riffing off a little bit of what Peter is saying, like if you look at PyTorch these days and you're using it to, for example, train a model in machine learning, it will typically end up using your GPU to be able to do this. And so at present, people just have to know how to use Python to be able to program in it. They don't have to understand the CUDA code that's actually running under the hood that takes advantage of the specific structures on the GPU that are being used to accelerate it. So if you're viewing quantum computing strictly as an accelerator model for classical computing, then it's entirely conceivable that the sort of approaches we've used so far for programming for accelerators should work just great for quantum. But again, the thing starts getting a little bit murkier as we start blurring the boundaries between the caller and the quantum. For example, if we want to take the classical calling program and put it in a quantum superposition, then things start getting kind of a little bit weird. But I think I would say I would be surprised if 90% of the applications that we're presently thinking about couldn't be handled in an accelerator model like that.
Eric, yep.
Yeah, one observation I have to add is that based on the private sector initiatives like quantum software startups, full stack vendors, they try to offer solutions which are as abstracted as possible in order to a larger user base. I think that this is all, too premature. In general, and if you have like, I don't know, a solver for a traveling salesman with a graphical interface, things like that, unless you really have a very solid understanding of the quantum advantage that allegedly or the signature that you're looking for, most of this productization should be probably not particularly of interest of NSF or the research community. I mean, eventually it will come for sure, because that's where the market pool is. I mean, once we figure out how to have a system that really actually does things in a quantum primacy way, which is reliable, scalable, and have like undoubtedly signatures of quantum advantage, then it will be productized in every possible way, abstracted for all the stakeholders, because that's where the value is. But I think that when it comes to the research community, we still need a lot of dirt access.
So putting on my former industrial hat, I gotta, I agree one aspect with David here is that, any sub 10-person large team that is claiming to deliver a full stack solution to quantum computing is just laughable. It's utterly laughable. And anybody who's going through with that doesn't understand the complexity of all the different levels and all the work that's needed in order to actually really be able to deliver on that. And, delivering a good full stack solution is going to be a monumental effort.
Do you think there's going to be a backlash after a while when people feel that they've been promised too much?
Totally. Completely. Of course, there's going to be a huge backlash where everybody in quantum has been promising the moon. And, sure, there's a ton of potential, obviously, but there's no way we can deliver, all the companies can deliver on everything they promised.
I think you're maybe, very dramatic in your opinion on this. There's a lot of value in trying to have, a visibility in every step of the stack, right? In every aspect of the stack. So, but yes, solutions. That's the problem. Like, we do not have solutions. Okay, it's not the full stack. The problem is the solution. Okay, we have a full stack approach to a future solution. Hopefully, right? That would be.
I mean, I think it's good to do some outreach. That's something we didn't do very much with Quicker that we developed, and some of the other teams are much better, at making a nice website with a tutorial and a pedagogical this and that. That's all very good. Yeah, I always felt this was way too early, because this is just a tool for specialists right now, like a tool for other researchers. But I mean, I think it is probably good to do that kind of outreach, and maybe some of the what you call productization actually makes that more attractive to bring more, as Martin was saying, sort of more more future quantum software engineers into the field. Maybe there's some value to that. I don't know. I assume there's some value to that.
Returning just for a second to the original prompt. I think that you can learn something just by looking at the recent history even of classical computers, like this proposal about no-code thing. It is true that computers today are easily programmable. but it's a truly modern development. Even back in like the 90s, if you were an end user and you wanted to run a video game, it's conceivable that you had to like know a particular incantation about interrupt requests to set up your sound card. And like the idea that like quantum computers that came online 5 years ago are going to be things that you just like point and click on feels very unlikely. In like the far, far future, yeah, sure. But even in like the medium term, like 20 years from now, I wouldn't bank on it.
So you think 640 qubits will be enough for everybody?
Yeah, the 640,000 maybe, yeah.
Yeah, okay.
I think 64,000. That's how I started in 1982. But it was bytes, not bits. So 64 kilo qubits. Are there even qubits? You never hear about qubits.
I wanted to give a chance for the audience to also ask some questions. So we already have one, but if others in the audience have a question, please either raise your hands or put your question in the comment box here. We'll read it out. But so the first one from Fahid is, I guess it's about the benefits and risks of developing a quantum computer. So what are the major benefits of reaching a fault-tolerant scale quantum computer? How will it benefit the world, solve unsolvable problems, and also how will it be risky? I mean, in terms of putting life in jeopardy and developing new weapons of mass destruction and so forth. So, anybody want to take that question?
All right, fine. I'll step on the landmine for you guys.
Take one for the team.
Yeah, exactly. Somebody's got it. So my take on it is that at the moment, quantum computing, offers a few radical changes for some niche areas, but it depends on what the specs are for the quantum computer. If we can get our quantum computers fast enough and cheap enough that a quadratic speed up is actually meaningful, then quantum computers will change just about every area we can think of, because it can give a quadratic advantage over brute forcing any problem in NP. So, that's one of the things that's huge. But at the moment, we don't think that quantum computers are going to be like that. A really fast quantum computer that I'd be super happy with would be like a megahertz. So at that speed, even if we do get to the 640 kiloqubit scale, I don't think we'd be able to play Doom on that thing. But nonetheless, we'd be able to change the world when it comes to simulation of physical systems, like in chemistry, or we'd be able to solve hard problems in quantum field theory that we presently couldn't do. And of course, we could ruin the world through fast factoring. But those would be the big ways that I would see changes happening with that. Now, when it comes to the actual ways that it could lead to weapons of mass destruction as a particular thing, quite frankly, I think the risks are minimal. The truth is that coming up with the closest thing to it we could end up doing is using it to simulate problems in nuclear physics. But already, if you take a look at the National Ignition Facility, they've got essentially analog simulators for those exact same things going on with their fusion machines that are being tested. And, we're not concerned about that so much. It's really the novelty of quantum that really ends up giving people pause at the moment. But the reality is that the risks are, I think, dramatically lower to society than a bunch of other things that we're looking at the moment. I think, quite frankly, targeted ads are much scarier than quantum computing is at the moment. Oh, I'm sorry, I'm getting funded by Google. They're perfectly fine.
No nefarious plans there. Well, what if, to put the question maybe slightly in different terms, what if government A gets a universal quantum computer first and government B doesn't? Will this give them a very significant advantage in sort of competition for world, I don't want to say world domination.
Domination.
National interest.
Are there any funding agencies in the room?
They are running this workshop, I guess, right?
Yes,
let me say one thing.
Safe is by paying me. Absolutely.
DARPA has launched a program called quantum benchmarking, asking exactly that question in a more rigorous way. But what is the utility of a quantum computer at scale? There are a lot of teams and with a lot of expertise working on trying to quantify, extrapolate, and get a better sense of the dollar value / the qualitative societal value and so on tens of instances which have been somewhat cooked to be how can I say, a proxy for the challenges that could be addressable by quantum computing. So I believe that nobody knows the answer to this, and probably Nathan has the best approximation to the true answer right now. But I believe that it's interesting how the U.S. government, as well as many others, are trying to really think about scenarios and extrapolate with some rigorous methods about the utility of these computers potentially. And I believe that there might be surprises beside the ones which are more intuitive. And I am particularly excited about the opportunity of some quantum machine learning applied, not necessarily only to quantum systems, but yeah.
Braver man than me, sir.
Yeah. So maybe I take a little bit now the opposite view again, because you talked about quantum computing. Can they use, or what can governments do with that in the sense of world domination? By the way, maybe not only governments but also companies or big conglomerates. But I mean, we talked about world domination, I, of course, not very seriously, but sort of like the huge prospect. At the same time, Nathan, you said before that there's so much promises around there, and maybe too much promises. And also, when you, for example, check out, the hype cycles of artificial intelligence as an example, but where it took decades with ups and downs. So a straight question, and we have to be a little bit short because we just have 4 minutes left. But what is your gut feeling about? Are we approaching a quantum winter? Is this hype or this momentum going down for a bit, or is it sort of like it may go down, but it still will survive? So what is this? So is this thing like in AI where it took decades with ups and downs, or is it sort of like we've got this momentum right now, and this momentum will be there also in the next years and decades? Maybe quick comments on that before we have to close up the panel.
Sure. I think that undoubtedly there's going to be ups and downs, and but one thing that I think is definitely true at the moment is that if you take a look at the hardware that we've got at the moment, companies like IBM have produced 100+ qubit devices, and I really thought, honestly, when I around the time I got my PhD, that I would see 60 qubit devices by the time that I retire. And so the level of, the promises are absurd. The level of growth in particular the hardware, and to a lesser extent in the algorithms, really has been, to some extent, justifies optimism that there could be something around the corner. I don't see a major slowdown happening unless there's a major economic shift, or B, a dramatic slowdown in the amount of progress that we're able to make experimentally.
Makes sense. Eric, David, Peter, maybe probably Peter's science agreement. Eric, Peter, Eric, David, any further comments? Last chance.
I largely agree, but I'm also too young to have like a nuanced opinion about this. I'm a latecomer, so.
I do agree. I want to say also that the talent that has been galvanized because of all of this period of hype is really a great societal benefit, because I believe that in general application of so many brilliant researchers, engineers to the quantum technology field will only result for positive outcomes for physics, computer science, and engineering eventually. So that's a very good thing that makes me very happy.
Yeah, I agree. And probably in general, it's hard to predict, particularly when it concerns the future, right? So it's always a little bit delicate. We're recording that, so maybe we don't want to hear what we're saying here today in 10 years from now, because probably the entire direction went totally different. Ali, do you want to close the panel?
Sure. Thank you, everyone. Thank you to all the panelists for your great insights. I really enjoyed it. And thank you to the audience. So we have a 2-hour break now where you can, I guess there's a link to join a Gather Town to hang out with everyone else. And then we pick up again in 2 hours with the final session. All right. Thank you.